Okay, so hi everybody. This is just a quick addendum to today's lecture on eigenvalues and eigenvectors and diagonalization. It's basically the content of section 5.4, which you need to know to do some of next week's homework, which has been assigned. So what's it about? So what we've done so far is we figured out how to find eigenvalues and eigenvectors, and also diagonalize n by n matrices. And as a linear transformation, an n by n matrix is a linear transformation from Rn to Rn. And what I want to discuss is how to do this for general linear transformations from one vector space to itself. So here's the definition. If T is a linear transformation from a vector space to itself, so again, previously we looked at transformations from one vector space to another. Here it's important that it's from V to V. That's the analog of being a square matrix. Okay, then some vector x in V non-zero is an eigenvector of T if the same equation holds, if Tx equals lambda x for some scalar lambda. So now I'm going to tell you how to find eigenvalues and eigenvectors of linear transformations, and also how to diagonalize them. Exactly the same thing will work, that if you use the eigenvectors as a basis, you'll get a diagonal matrix. I'm going to do this via an example. And the example is, I'm going to look at the linear transformation T from P2 to P2, defined by T of a polynomial is going to be T plus 1, little t plus 1, times the derivative of the polynomial. So remember, these are polynomials in the variable t of degree at most 2. So how do you find the eigenvalues and eigenvectors? Well, again, you use the correspondence principle. So step 1 is you just choose any basis for this vector space. So choose any basis for P2. For example, the standard basis 1 P squared. Then step 2 is to write the matrix with respect to this basis, right? We know how to do that. So the matrix of T with respect to this basis B, it's going to be a matrix whose columns are just T of the basis vectors, so T of 1 in the B basis, T of the polynomial little t in the B basis, and T of the polynomial little t squared, also in the B basis. And if you figure out what these are, well, let's just, okay, so if you differentiate the one polynomial, you get 0. So the first one is just 0. The transformation of the polynomial little t, well, if you differentiate that, you get 1. So it's just t plus 1. So that's the polynomial 1, 1, 0, coefficients 1, 1, 0. And for t squared, well, let's just do it over here. T of t squared is t plus 1 times 2t. So it's a polynomial 2t squared plus 2t. The coefficients are 0 to 2. So that's the matrix of T with respect to the basis B. And now step 3 is to find the eigenvalues and eigenvectors of this matrix. So, okay, what's the characteristic polynomial of this matrix? Well, okay, it's the determinant of minus lambda, 1 minus lambda, 2 minus lambda, and you have 1 and 2 over here. But this is an upper triangular matrix. I mean, at some level, we don't even have to do this since this matrix is upper triangular, we know that the eigenvalues is diagonal entries, but okay, why not? This is minus lambda times 1 minus lambda 2 lambda. So the eigenvalues are 0, 1, 2. No surprise, those are the diagonal entries of this upper triangular matrix. Okay. So once I have the eigenvalues, I can find the eigenvectors. So the eigenspace corresponding to 0 is going to be the null space of the matrix. Just 0, 1, 2, 1, 2. And the null space of that is actually just the span of the of E1. You have to do row reduction to find this. Let's call this V1. Then the second eigenspace corresponding to 1, this is going to be the null space of the matrix minus 1, 0, 1. Okay, you just get that by subtracting 1 from everything on the diagonal. And here, if you do row reduction again, you get that this is the span of the vector 1, 1, 0. Let's call this V2. Finally, you have the third eigenspace, E2, sorry, E3, the third eigenvalue is 2, which is the null space of matrix minus 2, minus 1, 0, 1, 2. And here, this is the span of the vector 1, 2, 1, which is V3. So these are the eigenvectors of the matrix of T with respect to the standard basis. But now, how do I find the actual eigenvectors of T in the vector space? Well, I use the correspondence principle, right? So what does it mean to be an eigenvector? Well, it means that this matrix T in the B basis times the vector V1 equals, okay, 0 times V1. But now, by the correspondence principle, that means T applied to the vector PB of V1 equals 0 times P of V1. And that is just T applied to the polynomial 1 equals 0 times the polynomial. Okay. So the first eigenvector of this linear transformation is the polynomial 1. Let's call that Q1. Similarly, the other eigenvectors correspond to PB of V2, which is, so remember, PB is this mapping from R3 to P2, which simply takes a coordinate vector in the B basis and turns it to an actual polynomial in P2. So PB of V2, and it's an isomorphic. It's the inverse of the coordinate vector. So PB of V2 is just going to be the polynomial 1 plus T. Let's call this Q2. And PB of V3 is just going to be the polynomial 1 plus 2T plus T squared, otherwise known as 1 plus T the whole squared. And let's call that Q3. So now the point is that, the correspondence principle tells us that these have to be eigenvectors of the original transformation, but let's just so I guess this was step 4 to translate back. And we can check this. So indeed, T of 1 is 0. We already checked that. T of 1 plus T, well, that's 1 plus T times the derivative 1 plus T, which is just 1 plus T. Then T of 1 plus T the whole squared is 1 plus T times the derivative of 1 plus T the whole squared, which is 2 times 1 plus T squared. So indeed, these have eigenvalues 0, 1, and 2. So this checked out. So the general approach for doing this to find the eigenvectors and eigenvalues of some linear transformation from vector space to itself. Choose any basis. And consider the matrix with respect to that basis. Find all eigenvectors and eigenvalues of this matrix, which is just a square matrix. And then finally, convert these back to vectors in V using the inverse of the coordinate mapping, PB. Which, okay, it goes, I don't know what n is, but let's say dimension of V is n, then this basis has n elements, and the coordinate vectors will be in R. And indeed, you can, the same thing holds. I mean, the same theorem holds if, I don't know, let's say V1 through Vn in V are a basis of eigenvectors of some linear transformation. So now these live in the vector space. Let's call this B. Then the matrix of T with respect to B is diagonal, and the diagonal entries are just the eigenvalues. So everything good that we did before, like the decoupling principle and so on, also works for linear transformations. And to do the calculations, all you need is a correspondence principle. You could try to just do it directly, but this is a systematic way to do it using the basically algorithms that we learned earlier. I want to make one more remark on how this relates to similarity. Suppose you have a linear transformation T from V to V, and you have two different bases, B and C. These are two different bases of V. Well, you can now write the matrix of T in these two different bases. And these will be different matrices. But by what we learned about change of coordinates, these matrices will actually be related by a change of coordinates transformations. So, for example, matrix of T in the B basis will just be the matrix of T in the C basis. But now you'll have these B to C and C to B coordinate change maps applied on both sides. But as we saw earlier, this is just a similarity transformation, right? This is just P of C get B inverse. So the point I want to make is that, yes, a linear transformation can be written in, has different matrices and different bases, but these are all similar. Okay? So matrices of a linear transformation with respect to different bases are similar. And this partly explains why in the method I showed you on the previous slide, it doesn't matter which basis you choose, because similar matrices always have the same eigenvalues, right? So this is why eigenvalues capture the meaning of the matrix. They don't depend on the choice of basis. They don't depend on the frame of reference that you use to write down the linear transformation. They're invariant under change basis.